Hi, college prep chemistry students. So today we're going to look at reaction profiles. Um, this is going to open up a couple of things for us. So we're going to be talking about thermochemistry, really big topic, something that's pretty big in like the AP chemistry course. We're not going that far, right? So we don't need to go as in depth as some of the stuff you may see. Um, I'm going to talk a little bit about the types of energy and the law of conservation of energy, and that can be a pretty big physics topic. So we'll see a little bit of review on that. It'll show up in our slides. So we're going to see a lot, and it can be confusing. And obviously, I would rather be doing this in class, but I hope that these slides and my examples help out. We will summarize everything at the end and what you need to know, so don't get upset if something doesn't quite make sense, because this is a really hard topic and it's a topic that a lot of people struggle with. We are not trying to do it all, right? We just want to have an appreciation for a chemical reaction profile, all right? And that will lead us into a little bit of thermochemistry, but it should be pretty okay. So let's look at our slides. So we're really focusing on the reaction profiles, but the reaction profiles include potential energy. So what potential energy is and why it's so important is something that you should learn by the end of this video. So potential. I love talking about potential. When we're on the second floor, I always tell everyone that they have potential, right? Because one form of potential energy is gravitational potential energy. The higher you are, the more potential energy you have, right? So in this picture, our skier in blue has more potential energy than the skier in red because the skier in blue is at a greater height. All right. So if you were to go to Six Flags and you were to ride King Ka, if you were to get stuck at the very top of that roller coaster, it's the world's tallest roller coaster, you would have a lot of potential energy because of how high up you are. Now, here we have an example of how kinetic energy and potential energy change, right? So if we were to think of like a roller coaster, at the top of the roller coaster, you have the greatest amount of potential energy. That's usually where you're going the slowest. But then when you go down the hill, you pick up a lot of speed, and at the bottom, you're moving the fastest. That's where you have the greatest kinetic energy. So here we have our biker. The biker has to put energy in to get to the top of that hill. At the top of the hill, the biker has a lot of potential energy, and then as they go down, they have a lot of kinetic energy again. So the potential energy converts into kinetic energy. They go back and forth. Now, this particular slide, I think it's interesting. Doesn't this kind of look like the shape of the energy profiles we have already seen? Because I believe it does. So think about it. We are at the bottom of the hill, then we have to put the energy in to get to the top, and then we get the energy out as we come down. So the law of conservation of energy. Energy cannot be created or destroyed. That's it. All right, but huge implications. So energy may change form. The total amount will stay the same for the energy, but it'll change form. So we can change from one type of energy to another. All right, so what are some of those different types? Well, for us in chemistry class, we're really thinking about chemical energy, and chemical energy is a form of potential energy, but chemical energy can be converted into motion. All right, you eat an ice cream cone, you go ride your bike. All right, chemical energy can be converted into motion when we think about a car moving. All right, radiant energy can be converted into chemical energy when a plant undergoes photosynthesis. All right, but all of these different types of conversions for us, chemical potential energy will be converted into thermal energy, right? Heat. So we'll be getting into that. So chemical potential energy. Energy due to the bond position between molecules. All right, it's stored during bonding. So that gravitational potential energy, the skier from the beginning of these slides, the position and how high up the skier is, that position tells us how much potential energy we have. Well, now it's due to the type of bonds being formed. Potential chemical energy is released from chemical reactions, burning, for example, right? So we can think of our foods as chemical potential energy. We can think of batteries as chemical potential energy, all right? And that energy can change form when we need it. But I want to come back to this idea of potential. So what does potential mean in regards to chemical potential energy? So I want to think in this picture, we're looking at runners, right? The picture on the left, we have the runners before they did the race, all right? They have a lot of potential. They haven't done the race yet, right? So they're good, they're fresh, they've warmed up, they've stretched, all that stuff, but they have the potential to do that race, all right? So they haven't given that potential away yet. Now, on the right, we see the runners after the race, and they look incredibly tired. They're laying on the track. All right. If any of you have ever had a really tough workout for your sports team, anything like that, you really pushed yourself in the workout, you know what it feels like to just be wiped out laying on the ground. All right. You've done the workout, and now you don't have the potential anymore. You kind of gave that potential away to do the workout. Right, your body, you were breathing heavy, you were getting really hot, you were sweating, all of those things. So if we think about the diagram, the runners before the race have more potential than the runners after the race, right? So the runners before the race, they have the potential. They do the race, all right? Now they're really tired. They're laying on the ground. They don't have as much potential energy anymore because they did that race, all right? So that's what's going on. All right, another example, fireworks, all right? Fireworks quite recently became legal in New Jersey, all right? So now you can find them when you're stocking up at your local grocery store. So we got these red, white, and boom. I always think the firework names are always kind of hilarious. But these fireworks, they have a lot of potential energy, right? When you light that fuse, they are going to explode. So these fireworks, before they've been reacted, have a lot of potential energy. They're going to be high on a potential energy diagram. Now, this is when they actually ignite. This is like that transition state. This is going to be the highest point on a potential energy diagram, right, when they go off. And then what's left? These are the fireworks afterwards. This is the debris, right? These fireworks here used to be these fireworks. All right, now, as someone who has to clean up on the beach every summer, all right, as part of one of my part-time jobs, there is a lot of debris on July 5th, so I always schedule to have that day off. I never work July 5th. That's the worst day to work. So again, the fireworks, they had a lot of potential energy before we used them, right? It's something that they had. And then they explode, and then what's left of the fireworks does not have a lot of potential energy anymore, right? And that would include the smoke, the carbon dioxide, everything that came out of those fireworks, right? But the fireworks after they're done, all right, don't have a lot of potential energy. The fireworks before did, all right? So potential energy is something that you have, and you can give it away, right? And so when you end up at your products, we kind of compare, well, how much potential energy do you still have now? All right. Now I want to think about, in our last two examples, we gave away that potential. Do you remember the lab where we made our own smoke bombs? All right. We mixed potassium nitrate and sugar, right? We heated it up, right? We stirred it up. We made that like brown kind of paste, and we put in the cups. All right. In that scenario, we actually, our reactants, the sugar and the potassium nitrate, did not have as much potential energy as the product we made, right? The smoke bomb. So this is an example where our reaction actually absorbed potential energy. The products have more potential energy than the initial reactants. All right. So how do we give away potential energy, or how do we gain potential energy? Because we saw earlier, law of conservation of energy, energy is neither created nor destroyed, all right? So it has to do with outside influences, all right? So we have two types of reactions. We have endothermic reactions and we have exothermic reactions, all right? Energy is conserved in chemical reactions. The total energy of the system is the same before and after. Now, an endothermic reaction, All right, it's typically a reaction where it is cooler. It is something that absorbs energy, and an exothermic reaction is something that we feel is hotter and it gives off energy. So on our diagrams, I know this is a little blurry, but on our diagrams, if the reactants have more potential energy than the products, all right, that amount of potential energy that we lose, right, it gets given off as thermal energy, and that's energy being released. We call that exothermic. All right, and if we go back, exothermic, think of like the flame, right? It is giving off energy. It has less potential now, all right, but it's contributed heat to the environment. And in a reaction where the reactants have less potential energy than the products, right? This is a reaction that gains energy, and it gains it from its surroundings. It absorbs the energy. So that is the endothermic reaction. Again, that's something that typically feels cold to the touch, but it is gaining energy. All right, when we made those smoke bombs, maybe it didn't feel cold, but we had to use the hot plate to transfer energy into the smoke bomb we made. So it gained energy. Its products have more energy than before. That is the endothermic reaction. All right, now what I want you to be able to do, I want you to be able to recognize these diagrams. If the reactants are higher than the products, I want you to say, okay, that's exothermic. If the reactants are lower than the products, I want you to say that's endothermic. They both always have the activation energy, right? That never goes away. There's always activation energy, all right? So here's a nice example of an exothermic reaction. This is cellular respiration. This is glucose combusting with oxygen to form carbon dioxide and water, right? We've balanced this as a combustion reaction. We have the activation energy, but then we release a lot of potential energy. It gets converted into thermal energy, but we release all this energy, and now our products are at a much lower position. They have less potential energy. All right, so the reactants have more potential than the products. The reactants are like those runners before the workout, right? They have the potential, but then they do the workout, and now our products don't have all that much potential. All right, now here is a nice example of an endothermic reaction. All right, we can see that the reactants, they're associated with this number 100, right? That's their potential energy. We put in 300 energy to get us to 400, right? So we had to put in energy as our activation energy, and then we release energy, but we only release 100 units of that energy. So we go from 400 to 300. So even though we've released some energy, we put in more than we released. Our products are now associated with 300 units of energy. So we still release some energy in the endothermic reactions, but we don't release as much energy as we took in already in the activation energy. So our products, they're at a higher energy state. They have more potential energy. This is an endothermic reaction. It has absorbed that energy. It has absorbed the energy that it took for the activation energy. All right. So again, I would want you to be able to, just by looking at the shape, tell me, okay, well, since it's ending lower than it started, exothermic. Since it's ending higher than it started, endothermic. Since it's ending lower than it started, exothermic. Now, on a graph, we can put numbers to it, and we can actually calculate what the activation energy is. That's the distance from the reactants to the highest point, right? The activation, the transition state. So the activation energy, it's from wherever we start to the highest peak, right? And then the amount of energy that's either gained or released is the difference in energy from the reactants and the products. Now, something I want you to notice, it's a positive number when it's endothermic. It's always a negative number when it's exothermic, right? Because we're actually losing potential energy because we gave it off as heat, as thermal energy. All right, now I want to shift gears here for a second. I want to think about a system and the surroundings. Every time we look at a chemical reaction, that chemical reaction is our system. And then the surroundings are everything else. All right, the surroundings might be the air around the chemicals. It might be the liquid if it's a reaction taking place in a solution. It might be the beaker itself. All right. So I want us to think the chemical reaction is the system and the surroundings are whatever are near it, right? But everything else pretty much. So heat, the general rule for heat is we say heat rolls downhill, right? What that means is heat always flows from a hotter source to a cold source. So more heat flows from the warm object to the cool object than from the cool to the warm. So the net is that the heat flows from warm to cool. So heat always flows downhill. It goes from something hotter to something colder. If they're at the same temperature, then we're at thermal equilibrium. All right. So think about it. If you put a really hot piece of metal in water, the water will heat up, the metal will cool down, right? But the heat will flow from the hot source to the cold source. So in an endothermic reaction, the surroundings are actually hotter than the system. So the heat flows from the surroundings into the system. All right. The surroundings as a result get colder. So a really important endothermic reaction is the reaction with Freon that takes place inside of an air conditioner, right? We need that reaction to cool off the air, and that's a very important reaction in the summer. That's an endothermic reaction where because the system is absorbing the energy, the heat flows from the surroundings into the system. Now, in an exothermic reaction, what actually happens is the system itself it becomes hotter than its surroundings. So the heat flows from the system outward into the surroundings. All right, the surroundings get warmer. All right, so that's something like a flame. If you've ever touched something that was hot, all right, that heat was transferred into your hand, and that's why it hurt. All right, and that's why you hopefully pulled away really quickly. But in the exothermic reaction, the system is actually hotter and it transfers its energy out into the surroundings. Now, here we have delta H greater than 0, delta H less than 0. We saw on those diagrams that the difference in potential energy, it was always negative when it was exothermic and positive when it was endothermic. So what is this delta H? All right, delta H is enthalpy. All right, it gets the symbol H, and it's the heat transferred between systems and surroundings during a chemical reaction. We can't measure the individual enthalpy of, let's say, the reactants or the products. We only measure the delta H, right? That's the difference in enthalpy. So that's the difference from reactant to product. All right. And so it's delta H, it's the enthalpy of the products minus the enthalpy of the reactants. Here's what you need to know, right? We're going to skip over some of this. Here's what you need to know. Delta H, when it is a positive number, that means that the reaction is endothermic. Heat goes from surroundings into the system. And when delta H is negative, that means it's exothermic. Heat leaves the system and goes into the surroundings. Now, enthalpy, it's kind of a fancy word. You can just think of H as heat, right? So if the change in heat is positive, heat goes from surroundings into the system. If the change in heat is negative, heat leaves the system and goes into the surroundings. All right? So heat, enthalpy, all right, they are the same thing. So delta H, that's just saying heat. Now, there's two ways we're going to see this represented. Heat can be listed as a reactant or as a product. All right, so reactants plus heat form the products. If heat is a reactant, that means it's being absorbed, and so the reaction is endothermic every time, right? So if you ever see heat as a reactant, it's an endothermic process. Now, if heat is a product, it's something that the reaction is giving off. So if you see heat as a product, it's an exothermic reaction every time. All right, so we have lots of examples on this page. All right, if we look at reaction 2, NaBr plus AgNO3 yielding NaNO3 plus energy plus AgBr, because energy is a product, this is an exothermic reaction. It's giving off heat heat is flowing from the system to its surroundings. All right. Now, if I look at reaction 7, for example, I have the NaC2H3O2 plus the PbO plus energy to yield PbC2H3O22 plus Na2O. Because energy is listed as a reactant, this is an endothermic reaction. Heat or energy is actually going to be absorbed by the system, and the products will actually probably feel colder to the touch, right? Because energy has moved from the surroundings into this system. All right, so endothermic. All right, so again, delta H greater than 0 means that a positive number means it's endothermic, and if delta H is a negative number, it's exothermic. The other thing we will see, the reaction will be given and the delta H will be given. All right. So in reaction A, delta H is positive. That means it's endothermic. That means that this 181 kilojoules and the kJ, that is the unit of energy, that would be the reactant. So it could be N2 plus O2 plus 181 yields 2 NOs. Now, in reaction B, the delta H, it's a negative value. That negative value means it's exothermic, which means that's the energy that is being released, all right, as a product. So the two NO2s yields N2O4 plus 87.6 kilojoules as a product, right? That would be the product. All right, so the delta H is negative when it's exothermic. And in C, we have a negative delta H, it is exothermic. So if you are given a delta H, I want you to be able to tell me if it's endothermic or exothermic. That means if it's positive or negative. All right, so if you see that negative delta H, that's hot. All right, that's real hot. So just be on the lookout for that. All right, so in conclusion, if we're looking at this diagram, we should have an idea of what potential energy is. All right, the higher up we are on it, the more potential something has. All right, the lower we are, the less potential we have. Now, we always have to input energy to get to that transition state. So we always have to include energy to break the bonds of the reactants, right? Energy always has to be put in. That's our activation energy. And then we always release energy as we form the products. It's just a question of how much energy do we release. If we release more energy than the reactants we're associated with, then we know we have an exothermic reaction, right? Products are lower than the reactants. And if it was higher up, we would know it was endothermic. So anytime you see a reaction profile, I want you to be able to understand what's going on. All right, so that's the important stuff. I want you, when we see these graphs, I want you to know what you're looking at, and you will be drawing your own graph in this week's weekly assignment. All right, you'll be drawing it for a reaction. You have to make sure that if it's exothermic, your products are lower. If it's endothermic, your products are higher. You'll have to look that up. All right, and I want you to draw what the molecules look like at each point: reactants, transition state, and products. All right, so again, this is everything you need to know this week about the reaction profiles, potential energy, enthalpy, which is just heat, and the chemical potential energy.